Good. And so today, as I promised you, we are going to learn about something called continuity. Continuity. This part. Okay. What is it actually? And probably I'm going to also teach you about differentiability, because believe it or not, there are some function that is not differentiable. Differentiability. Okay, there are some function that has no limits. We've seen it before. There are some functions that is not continuous. We will see it. And there are some functions that are not differentiable. Why do we need to know about differentiability? Because we are doing calculus, remember? Because we're going to do calculus, and then we need to know about what can be differentiable, so that we can apply antiderivative. What if we can apply that, then hopefully we can apply antiderivative as well. Okay, so I'm going to show you these two new topics today. New topics. Okay, continuity. So what is actually continuity? So if you can write this down, in simple words, you can write this down in your notes. In simple words, a function is continuous. A function fx is continuous if the graph has no gaps or jumps. Okay, example, if you have a graph and then there is a gap here, there's a gap, and then we continue it here. So there's a gap here. Okay, there's a gap. So that means it's not continuous. There's a hole in there. All right. Or if your function has a jump, for example, like our Heaviside function just now, we have something like that, and then at the same point it jumps up towards here. So here is what we call jumps. Okay, so these functions that have gaps or jumps or anything in between, or have gaps, both gaps and jumps, not anything in between, sorry, both gaps are considered continuous. The same thing that the example, the piecewise function that I showed before, where you have here and then it's a straight line, but at one point it just jumps up to here. So this one is also not continuous because it has gaps. Okay, so this is an easy way to look at continuity of a graph, because we can inspect the graph using visual. If you can plot it in Wolfram Alpha or your calculator, you can see if there's a gaps or jumps. But what if we cannot see the functions? We're only given, for example, algebraically, how do we do it? Okay, so formally, mathematically, okay, we need to say a function f is said to be continuous at point A if the following conditions hold. Okay, it needs to satisfy this 3. Okay, f is continuous at A only if it satisfies all these 3. First, the limit of the function when x approaches A exists. Okay. Secondly, the function at point A also defined. Okay, if it exists but it's at infinity, then it's not really defined then. Okay. And finally, the limit of the function f of x when x approaches A is f of A. If it satisfies all these 3 conditions, then you can say f is continuous at point A. Okay, so this is the formal mathematical definition of a function continuity. All right. So let's see if there's any examples. Okay, I hope you can see this. Wait. Let me see if I can do this like here. Okay, now there are two functions. If you look at the left hand side, you know, it's a straight function. The function equals to 1 whenever x is not equal to 0. If x is not equal to 0, then it's equals to 1 always. And if if x equals to 0, then f of x equals to 0. So there's a in this case there is a jump. So that means this function is not continuous in this interval. Okay, so between this here, we know it's not continuous here. This is the point of discontinuity. Okay, now if we look at on the right hand side, is it continuous in this interval from here to here? Is it continuous? We see no jumps, no gaps, so that's a good thing. Is it continuous at A, for example? Okay, and then we see at A, limit when x approaches A, that this fx, well, it exists. F of A is defined here, a squared, okay, it's defined, and limit of the function as x approaches A is f of A. So it satisfies this, and it also satisfies our visual inspection here. It also satisfies our formal definition of continuity just now. So we call this function is continuous in this interval. Okay, so that's nice. So this is an example of a discontinuous function and an example of a continuous function. Okay, so let me see. Let me ask you here. I need your response here, yeah? Okay, I need your response here. In this case, I give you 5 plots, asking you to find the points of discontinuity. Okay, I need you to, maybe I need to copy image and then put it in this one so that I can get your response. Let's go to assignment help. Okay, find the discontinuous functions that are not continuous. Okay, so let me not continuous. That's the question, and then let's find A. Okay, let's get some going on. Find the functions that are not continuous. A, B, C, D, E. So only pick the one that is not continuous. Not continuous. I think this is too easy. I think everyone gets it. Yes. Nice. Very nice, everyone. I think it's pretty simple concept, yeah. Yeah, I think this topic is easy. All right. So find the points of continuity. So you say that B, C, and E, B, C, and E discontinuous. So find points of discontinuity. So in this case, the point of discontinuity is here. Okay, looks like when x equal to 0, f of x have some value, but there's a discontinuity here. There's a gap here. There's a jump. Okay, now that's correct. C, is it discontinuous? Is it not continuous? Yes, it is not continuous, because at point 1 here, there's a gap. There's a gap here because we are actually, any asymptote, vertical asymptote or horizontal asymptote even, okay, if it exists, that means it's not continuous. So we can see the point of discontinuity here is at point x1, because that is where the function from left hand side is approaching minus infinity, and from the right hand side it approaches plus infinity. We can also say that the function of the limit of this function is non-existent at when x approaches 1. Again, this function, the limit of this function is non-existent, does not exist when x approaches 1. The reason is because when you approach from the left hand side, it goes to minus infinity, approaches from the right hand side plus infinity. So it's not the same. So there's a gap here. It's not only it's not continuous because the limit at this point doesn't exist. Now here, although we see there's some, the sharp points here, just like this case also, there's a sharp point here. It's weird, but it's still continuous. It doesn't have any jumps. It doesn't have any gaps. Same here as well. It doesn't have any jumps. It doesn't have any gaps. Here, obviously, I think that's too easy. Okay. Now I'm going to give you another definition. Okay, there's a definition here. Is a general. Yeah, the function f is said to be continuous at a if the following conditions hold. Okay, now we can also say that continuity over a closed interval. Interval means a range in x. Interval, just like this. The informal range in, not range, because I don't use the range. Range has different meanings in mathematics. Okay, this is what we call interval. Between these two interval. Okay, we usually write it like this: f with square brackets if it include A and B, or if we do it like this. Okay, all right. So the form is, let's say for example, you have something like this: round bracket B, okay, include B, not A. So A in this case, it's like this. Okay, or some other things, if you can see intervals defined like this. So this include B, A, not B. Okay, usually written like this. Okay, now if A that, so this means that it doesn't include A or B, so it's like this. Okay, so this is how you define an interval. So sometimes there's a function that is it's only continuous in an interval. Okay, so there's a formal definition here. You can write it down in your notes. Function f is continuous over interval a b if, remember, pay attention to this square bracket. I'm using square bracket here. Oops, I'm using square bracket here. Okay, if A is continuous at each point of the open interval AB, notice the bracket, round bracket. Okay, F is continuous on the right of A, right here, that means right here, and F is continuous on the left of B. Okay, just okay. Like I said, this is all, you know, in writing. Okay, mathematics can be explained in writing, but sometimes we also can learn a lot from visuals. Okay, so let me provide you some visuals. Okay, not this one, not this one, not this one. This one we have seen it before. Oops, did I miss a thing? Oh, here it is. Okay, so for example here, okay, we can see that this function here, okay, this function, if you look from this interval until here, it's not continuous. The reason being because there's a gap here. See, there's a gap there, so it's not continuous over this what the intervals that we see here. But okay, but if we look at the function between this interval a b, okay, we see that it's all continuous. So we can say here is f is continuous at the interval a and b, ab. So usually when you use square bracket here, it means include a and b, and usually when you include a and b, the dot here is blackened. Okay, so we can say it's all, but it's not. Let's say this is what number is this? Let's say this is C and this is D up here, D. Okay, we can say f is not continuous at the interval C, D. The reason being is there exists here. Okay, so you can say it's continuous, but it's continuous on these ranges only, at the interval, this interval only. But if we, let's say we expand the intervals from to C and D, expand it, say it's not continuous. Okay, so that's easy. Here is another example. It's continuous up until the point. Okay, so if you, let's say if you define your, let's say if you define your interval here, this is a b. Okay, so this is your interval x. Okay, as you can see, obviously there's a gap here, there's a jump here. Okay, so this function is not continuous at the interval between a and b. Okay, what about this is something for you to think about. Okay, let's say this is 0 and this is 0.1. Okay, is f continuous in the interval 0, 1? Okay, is f continuous from 0 to 1? Okay, so what I want you to do is you look at this question, this picture, and then look at the definition just now, and then determine whether it's f is continuous at 0, 1 or not. Okay, so that's a practice for you. Find out the answers, because usually I like to, in exams, I like to give some graphs and then you analyze that graph, something like this. Okay, so that's that. Do you have any questions before that? Let me stop here. Do you have any question? Is everyone still here or dah tidur dah?
Ada doktor.
Okay.
Yeah.
Alright. Okay, don't worry ya. Nampak dah macam letih tu. We're gonna stop earlier today, probably 11:30. I'm not going to go 2 hours. That'll be crazy. Okay. So now, oh man, no. What is this? Sign out, reload. I hate this. Why do I get signed out in the middle of a lecture? Now where's my... Oh no. Okay, here. Phew. Google Keep is notorious for deleting my notes, yeah. Oh, okay. Before that, so let's go back to what I promised you just now. I promised you that I want you to teach you about limits, about continuity. For limits, we have done exercises, we have looked at the theorems, we have looked at the applications when, in calculus. That's nice. Continuity, we have looked at the examples. Okay, now differentiability. What does it mean when a function is differentiable? Or what does it mean when the function is not differentiable? You cannot find the derivative, for example. Okay, so I want to explain this in terms of visuals. Okay, I think it's easier that way. Look at this. There are 3 instances where a function is not differentiable at a point A. Okay, there's only 3. When you have a corner like here, something sharp, okay, it's not smooth, cusp of corner, so you can say this function is not differentiable at A because the reason is it's not differentiable at A because the reason is you have a cusp or corner here. Okay, and this at A only is differentiable everywhere else. Okay, no worries, you can differentiate here, it's fine, but at that point A, it's not differentiable. Whenever it's discontinuous, oh my god. Okay, whenever there's a discontinuity, like here, there's a gap, there's a jump here, so you can say that function is not differentiable at point A because there's a gap. Okay, so if you want to find derivative of this function at point A, you won't be able to because it's not differentiable. Another thing is when you have what we call a vertical tangent. It's a straight line. It's a straight line, a tangent where, you know, the slope is infinity. So when the slope is infinity like that, the function is not differentiable at that point. Okay, it's differentiable everywhere else but not that point. Okay, so only three instances here. If there's a corner, sharp corner like that, or there's a gap, there's a jump, it's not differentiable. Or whenever you find there's a tangent, it's totally vertical when it's the slope of tangent is infinity. Now those are 3 places where the function is not differentiable. Okay, so let's look at some examples here. Let me see. Okay, did I do this? Okay, yeah, just now I shown this here, but let's take a look at we talk about discontinuity. Okay, but let's talk about differentiable. Now this function is differentiable everywhere except at this point. It's not differentiable at that point. Same here. This function is differentiable everywhere else except that point. Same here. It's differentiable everywhere except at point x equals to 1. Not differentiable. This one is also differentiable everywhere except at point when x equals to 0 because there's a sharp corner there, and x equals to 1, because again there's a sharp corner there. So it's not differentiable at 2 points, here and here. Oh, now here this is terrible. Ya, apa soalan ke? Oh, sudah. Perhatikan, you okay? Alright, I hope you're okay. So this one is not differentiable here, not differentiable here, not differentiable here at that point, not differentiable here at point number 3. So at point number 0, here I think, what is this, -2? It's here, not differentiable, not okay. So that's easy. Alright, so now let me, this is an example of exam question. Okay, so usually it's just probably just one of the multiple choice question. At which point, okay, you're given a function, it's a piecewise function, okay, 1 over x plus 2 if x less than -2. It's equal to 10x squared when x is between -2, x, so on and so forth. Okay, and 50x whenever x is more than 0 here. Okay, please tell me at which point is f continuous but not differentiable. It's continuous but not differentiable. Let me know. Let me know. Yes. Correcto. So the point here is continuous, but it's not differentiable. At which point is f continuous? F not continuous and not differentiable.
X negative 2.0.
-2.
It's not only continuous, it's not continuous, and it's not differentiable. Okay. Is there any point that you can think of where f is not continuous but differentiable? It's not continuous but differentiable. Is there any case you can find?
No.
Are you sure? So that's your homework. Find a case where a function is not continuous but differentiable. Is there such thing?